right, so today we're talking about the volume of pyramids and cones. Yesterday, or in the last lesson, we talked about the volume of a prism or cylinder, and what essentially we're doing there is we're taking some two-dimensional shape, and then once we found the area of that shape, we're going to stretch it into a third dimension and say, well, the volume of that shape is simply, and we get, whoops, what was I doing here? We get that the volume is just the area of that base times the distance between those bases, or the height. So that's essentially what we did when we found the area of a rectangle, right? We say, okay, we take some length, let's call this the base, and then we take this and stretch it into a second dimension and say, well, now we've got that base stretched through this dimension, and its height long, so we go base times height, is the area of this rectangle, right? Today's lesson is just saying that the volume of a pyramid or cone is actually exactly 1/3 of the volume of an equivalent prism. Or in other words, if I have some base, and I know the area of this two-dimensional base, right? I have two copies of it, one here and one here. Same exact base, congruent, same area. If I connect one of these bases to its congruent base above it, I go, oh, yeah, well, the volume of this prism is base times height. If I connect all the vertices instead to a single point, this pyramid is exactly 1/3 the volume of this prism. So this is equal to 3 times the volume of the prism, or pyramid. Now that, to me, is one of the most beautiful things in math, how these relationships come out to be things like 4/3, 1/3, pi, these beautiful numbers, not just some random decimal, right? Not 0.276 times the volume of the prism, but exactly 1/3. Now, we're going to just look into a little bit of the why, but I'll fully admit this is one of the only topics in geometry that I cannot boil down without calculus or limits or, some big assumptions like, well, let's just look at a cube. But for any prism, it's hard that this is one thing I can't simplify down and say, well, here's a nice, simple geometric or algebraic reason why. And it's just a thorn in my geometric paw. But this is the beautiful thing that's going on. So let's say we just take a right cylinder here. It doesn't have to be right. It doesn't have to be a cylinder. But let's just use this as an example. Okay, and let's say we take this base at the top and we connect it to a single point on the bottom. So here we get a cone, okay? Then we take another from the bottom, let's take a different color. We say, okay, well, let's take this bottom thing. Oh, those colors are pretty similar. Let's take green instead. So we take this base here and we connect it to a single point on the top, and we connect it and we get another cone. Now you might be like, but Mr. Dilloughery, that takes up all the space. But it doesn't. It just appears to from the side. If we actually take a plane here and we intersect this parallel to the base, what we end up getting is we get this cross section here of a circle. And if I flatten it out and say, well, what does that cross section look like right there? I get, just to switch the same colors, I get a blue circle with a purple piece, right? A circle, because this cone right here is a circle where it's intersecting the plane. And that's got, its own area there. And then we've got this green one that's also a circle, right? This is just a circle right here. But what is interesting is, so if each of those is 1/3 the volume of the cylinder, the craziest part is that means all this leftover slop, right, that doesn't have some pretty shape. I mean, it's a circle taking away 2 circles, and they're all stacked up. So at the top, there's no leftover space. And then if you take a slice out here and look at what it is, it's going to be mostly missing this big purple area and then missing a little green area, and there's not going to be that much extra space. And then the closer you get to the center, you've got lots of extra space. And then down at the bottom again, most of it's taken up by the green. But if you add up all that extra space in there, it's exactly the same volume as either one of the cylinder, or cones, so all three have exactly 1/3 the volume in them. And the why I had not been able to, for the life of me, figure out a simple algebraic reason why. I mean, yeah, you can use calculus and find the rate of change of these things. You can use the slopes of these sides of, these cones in, the 3-dimension, like how much is the rise over run. You can use the height but still, like, even using all that in proportions and what portion of this wedge is missing, and there's that many wedges stacked on top of it, I just can't for the life of me find a simple reason why. And it's just a beautiful topic to me. Okay, so you could do the same thing for any prism. So here's a trapezoidal prism. So if I just connected this base to a point on the bottom over here, and then I do the same thing from the other side, let's do this base here, and we connect it to this corner up here. So what we end up getting with any cross section we take, I'll do a totally different color here. Let's do purple now. If I take a cross section of this in the middle, this cross section will be missing a green trapezoid up here in the top part, and then it'll be missing a red trapezoid down here in the bottom part. And all that leftover area will also add up, all that leftover volume will add up to 1/3. So cool. But our formula is, for every cone and every pyramid, the volume is 1/3 the area of the base shape times the height. So cool. Okay. Now, one thing to note is not the slant height, right? The slant height is on the surface. We use that for surface area. We could definitely use it with either trig or Pythagorean theorem to find the height, but the height we're talking about is perpendicular to the base, not along the edge, right? Okay, so down here, let's do a couple examples. So number 3, pretty straightforward. We say, okay, well, the volume is 1/3 the area of the base times the height. Now it gives us the height here, perpendicular to the base. The height is 6. The base is a rectangle. We can tell from the right angle and the 4 congruent sides, or a square I meant, 4 congruent sides and a right angle. So that would mean a rhombus with a right angle, meaning it's a square. So there's 1/3 of, and base times height of that square is 5 times 5. So 1/3 and 6 cancel, leave 2. 5 times 5 is 25, and so we get a volume of 50. Okay, over here we've got, this is still volume is 1/3 area of our base times our height. So this time we've got the area of our base is pi r squared, or pi 10 squared, times, and our height is 13. So this is 1/3 of 100 pi times 13. Too bad there's not a 1/3 that comes out. There's no 3 in there. So this is going to be 1300 pi over 3, and that won't simplify at all. But you could plug it into a calculator to get an approximate value. Okay. Now here, I want to look at these because these are really common mistakes. So for number 1 here, we've got, let's see, 1/3 the area of the base times the height. So we've got the 1/3. We've got pi 9 squared. Let's just double check. 9's the radius. This is the base. That seems to look good. Height of 15. And oh my goodness, look at that. They used, this is the slant height. We only use the slant height with surface area, not with volume. With volume, we care about how tall the shape is. We don't care in what direction, if it's steep, if it's not very steep. We just care how far away is this top point from the base. It could be overhanging, right? I could have a pyramid or cone that looks like this, but we still measure the height perpendicular to the plane of the base. So if we want to find that h here, we got to use Pythagorean theorem. So we would say h squared plus 9 squared equals 15 squared. But I actually recognize this is a 3, 4, 5 triangle. Or using Pythagorean theorem, we get that h is 12. So if you go back here and just plug in a 12 here instead of a 15, everything else was great. They just accidentally used the slant height instead of the height of the cone. And that's a really common mistake. Okay, so let's look at the next one. So it's 1/3 area of the base times the height. We've got a height of 10, check. We've got a base that is a rhombus. I guess we're going to assume it says right cone or pyramid. It doesn't say regular, but we're going to assume this is not a rhombus, but is a square. So the area of that is 7 times 7, or 49, check. But it's that 1/3. They accidentally thought it. We're thinking of like 1/2 base times height, or 1/2 apothem times perimeter. So a lot of formulas we use that have a 1/2 in it. So they missed that 1/2. If you cross that out and replace it with the 1/3, that was great. Okay, let's go down here. So anything we do forwards, we can always do backwards. So let's say 13 for no apparent reason here. Let's do, so volume we know is 1/3 area of base times height. I'll switch to blue here and plug in what we know. Well, we know the volume is 216 pi. We got the 1/3. The area of the base is pi r squared. Our radius is x, so this is pi x squared. And then times the height, and they give us perpendicular to the base. This isn't the slant height. They give us, this is 18. Okay, so I know that 1/3 of 18 is 6, so just this is 6 pi x squared equals 216 pi. So before I square root to get this x to be just x and not x squared, I want to get rid of all the numbers that are by it. So let's divide by that 6 pi, because 6 pi is just a number. It's around 18, but we divide by the 6 and the pi. So the pi cancels out. 216 divided by 6 is 36. Equals x squared, and we take a square root. Now, technically, it should be plus or minus 6, but since x is a real distance in the real world, it can only be positive. So x has to be 6. Okay, so over here, this is a little longer, but I want to jump into this. So on the bottom, we've got an equilateral triangle. Now, we could, because every face is a triangle, we could choose any side to be the base, and then multiply by the corresponding height. But we only have one height, right? Perpendicular to this base right here, we know the height is x, so we're going to choose that bottom side as the base. If we had something perpendicular to the right face, we could absolutely choose that face as the base. Okay, so we've got volume is 1/3 area of the base times the height. So back over here, we've got 7√3 equals 1/3. We're going to have to do a little work to find the area of this base times the height of x. Okay, so let's go down here and see. So we've got an equilateral triangle, and each of the sides is 2√3. And I know all the angles are 60 and 60. And anytime we even have an isosceles triangle, anything that's symmetrical, we're going to go ahead and immediately cut that in half. So if I cut that in half, I know I cut the 60 at top up to 30 and 30. And so now I can use a 30, 60, 90 triangle here and say, well, in my 30, 60, 90 triangle, I have 2√3. And I'm looking for, oh, I have a 2√3 on bottom. So this is a single √3 and a single √3. So I already have a base. I just need my height here. And I know this is similar to every 30, 60, 90 triangle, specifically the one we use a lot. That's 1, 2, and √3. So I can notice right away that they are similar by a scale factor of multiplying by √3 or 3 to 1. So if I want to find h, I just multiply √3 times √3. So h is √3 times √3, or h is square root of 9, or h is 3. So that gives me my area of the triangle is 1/2 base, which the entire base of the triangle is 2 √3s, √3 plus √3, just like x plus x is 2x. So the entire base times the height, which is 3. So that is, the area is 3 √3. So now I can take the area of that triangle and go back up here, because this was the area of my equilateral triangle. So putting that in, I was 3 root 3. So 1/3 of 3, that cancels. And what we've got is 7 root 3 equals root 3 times x. Well, if we just divide both sides by the number next to x, right, we get x equals 7. So a little harder just because we had to find the area of an equilateral triangle, but the same steps. Okay. So we can always fall back on our trig too. So here are, I don't want to do the 15 because we've already done some 30, 60, 90 triangles. But let's look at 16. We want to find the volume of the right cone. So V equals 1/3 area of the base times the height. What do we have? Well, we have this entire diameter here is 14. So that means that the radius is 7. So I know that I can do the area of the base circle is pi times 7 squared. So what we're really looking for is the height. Okay? So I can see that there's a right angle here. I got a 7 and an h and a 32. Now, since this is a right cone, I know that this center, or this point or apex of the cone is directly above the center here. So that means that this is a 32 degrees in every direction. It's symmetrical in any direction since the point is in the center, if you think about turning this upright. Okay, so now we've got, just I'll draw it down here. We've got a 32 degrees, a right angle, an h, and a 7. So I'm going to use some SOHCAHTOA, and I'm going to say, well, that's the tangent of 32 degrees. That's equal to my opposite over my adjacent. And then I'm going to multiply by whatever's on bottom. So multiplying by h. Then I'm going to divide both sides by tangent 32, because tangent 32 is just a number. This is a number times h, and I want to get rid of the number. So I divide by the tangent of 32 on both sides. And I get that h is equal to 7 divided by the tangent of 32. I go back and plug that in up here, and what I get is 1/3 of 49 pi times 7 divided by the tangent of 32. And this did not work out pretty. That's a little too ugly for me to leave it as an exact answer. So what I'm going to do is I'm going to figure this out to the 2 decimal places, so to the 100th. So I'm going to say this is approximately, let's pull this over, this is 1/3 times 49 pi times 7 divided by tangent of 32. Let's see how that works. There we go. Oh, it figured out there's a 49. There we go. Look at that. Okay, so 574.82. 574.82. There we go. Okay, so we can definitely use trig to find a missing thing. Just over here, we have the slant height. So if we want to go and find the radius or the height, what we need to do is use that trig and say this is 54. So, cosine of 54 would be r over 15, yada yada, to find radius. We'd say the sine of 54 equals the height over 15, yada yada, to find the height. And then it's v equals 1/3 area of the base, or pi r squared, times the height, right? So that's just to get you started with a kind of plan there. All right, so the last types of problems we'll be talking about are composite shapes. Very often we'll be dealing with composite shapes, especially with volume, because unlike surface area where certain parts get covered, and then you have to think about, okay, well, I want the lateral area of one plus the, the base of another plus the lateral area, and that gets complicated with surface area. I mean, those are beautiful problem-solving skills. But with volume, it's a lot easier. You're essentially saying, I've got a conical or cone thing up top that holds 1 gallon of milk. And it's sitting next to this big giant soda can that holds 2 gallons of milk. So 2 gallons plus 1 gallon, together my 2 containers can hold 3 gallons of milk. Doesn't matter if the containers are sitting on top of each other or next to each other or apart from each other. We just say how much volume they can add up to, right? And then similarly, over here, we essentially have one giant tub of ice cream. And we say, wow, man, this started with, I don't know, like 10 pints of ice cream. And then we take a big spoon in, and this spoon happens to be shaped like a pyramid. And we put that spoon in and dig out some ice cream and go, nom, 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 that was delicious. Well, now instead of 10 pints of ice cream, we have 10 minus however many pints we ate. If we ate 3 pints of ice cream, that's a 3-pint whole. So now we have 10 minus 3, 7 pints left. So that's the main thing we're doing here. So the big picture is I'm going to take the volume of this cylinder that's on bottom, right? The cylinder being this bottom part here. I'm going to find the volume of that. And then I'm going to add it to the volume of my cone, right? That's the main thing we want to do. Okay, I won't do all of these because then there's 3 more down here. I'll kind of pick and choose which ones to do. For the next one, we want to do the volume of this rectangular prism, which happens to be a cube because it's 10 by 10 by 10. And then we're going to say, starting with that, we're going to actually take away the volume of this square pyramid that's upside down. Okay, over here, we're just going to say, oh, look, I've got the volume of a bigger upside down cylinder. And I'm going to add the volume of a little tiny cylinder. Okay, down here, I'm going to say, well, it looks like I've got 2 square pyramids together. So I've got the volume of the top square pyramid. And I'm going to add it to the volume of my bottom square pyramid. Over here, I've got the volume of another cube. And I'm taking away from that the volume of a cone. Over here, I've got the volume of a cylinder. And I'm taking away the volume of a, and if you count that up, I believe it's an octagonal pyramid. So the big idea being, are you putting 2 things next to each other, or are you scooping out some volume that was already there? So I'll just do a couple of these. One I think is interesting is 21. So I'll do 21 here. So 21, volume of the cube. So let's say this is a rectangular prism, not using any shortcuts. Let's call this the base. So we've got the volume of any rectangular prism is the area of the base times the height, because that's a prism. The base is 10 times 10. And then the height from base to base is also 10. So that is 1,000. And then minus, now here's where it gets a little tricky. So I know any pyramid or cone, it's 1/3 the base times the height. Since it goes from this top plane to the bottom plane, I know it's got the same height as my cube, so it's minus 1/3 the area of that base shape times the height, and whoops, times 10, we just found the height. But the main thing here is, so often the hardest part is finding the area of that base. So what we need to do is find, what is the area of this base right here? So just to lay it flat and see what we're dealing with here, we've got a 10 by 10 by 10 by 10 square. And then we connect, because I can tell by all these markings that I'm using the midpoint of each side. So I'm connecting the midpoint of each side to make, I don't know, looks like a square. Let's not make any assumptions. So that's 5 and 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 5. So let's go ahead and erase these 10s here. Okay, so what types of triangles are we dealing with? This was originally a square, and we've got an isosceles triangle on each. Well, then this must be a 45, 45, right? Because these 2 angles match. And this is 45, and this is 45. and this is 45, and this is 45, and this is 45, and this is 45. And then we can use isosceles right triangles, or 45, 45, 90 triangles, or Pythagorean theorems to figure out that all these have to be 5 root 2, 5 root 2, 5 root 2, 5 root 2. And then what angle is there? Well, out of 180 degrees, take away 45 and 45. In other words, take away 90, and we're left with a 90, and a 90, and a 90. So this is a square. And the area of this square, so the area of the base, is equal to just base times height, or 5 root 2 times 5 root 2. The easiest way to multiply these is rearrange the order as 5 times 5 times root 2 times root 2, or 25 times root 4, or 25 times 2, or 50. And once we have that, we just plug that all the way back up into here. We say, all right, now it just becomes simplification. So, earlier I'd written 100 there. That was not good. So this is 1,000 minus 1/3 of 500. So that'd be 3,000 thirds, finding the common denominator, minus 500 thirds. So altogether, that's 2,500 thirds, or just a little over 800. Okay, maybe one more example here. Nothing tricky here. It's just 1/3 big base times height. It gives you everything you need, plus 1/3 little base times little height. But again, you have everything you need. On number 20, you have everything you need. Let's look. Yeah, you're given everything you need here too, right? The area of the base times 1/3 times height. It's just a square, so 3.3 squared. The height of both is 2.3. Let's look at, I guess 24 and 25. Let's do them both. So volume of the cube here, again, just like above, let's just choose the bottom as the base. So 5.1 times 5.1. And the height is the same height as the cone, which is 5.1. So, okay, 5.1 to the third power is 132,651. Okay, and that was exact. There's no ... there. We're going to take away 1/3 area of the base times the height. So minus 1/3, and we need pi r squared times the height of 5.1. So we just got to find r here. Well, we know that this square is 5.1 across, and this circle appears to be tangent, and that's one of the assumptions we can make in geometry. If it appears to be tangent, it is. So that means the diameter is 5.1. So half of 5.1 is 2.55. Just to double check that. Yeah, 2.55. So we're going to go down here and go 2.55 squared. And that's it. I'll leave the arithmetic up to you guys there. So the last problem, and this one's just a little harder because it has us finding the area of a regular polygon, is going to be, well, volume of a cylinder. That's just area of base times height, or pi r squared h. It gives us the r squared, so this is pi times 2 squared times height of 3, or pi times 4 times 3, or 12 pi. Okay, so 12 pi, and we're taking away 1/3 the area of the base times the height, or take away 1/3 of the thing we're looking for times 3, because the same height as the other, and 1/3 of 3 cancel. So really we've got 12 pi minus, and this is area of octagon. And now we just got to find what the area of the octagon is. And again, that's really common. That was the same thing as up here. Finding the area of that base, same thing as up here. Finding that, that wasn't it. I meant up here. Finding the area of the base can often be the hardest part of a problem. So let's just do that problem really quick. So I'll draw out my octagon. Now I know that to find the area of a shape that is regular, I can use the formula the area is 1/2 apothem times perimeter. Another way to do it is just cut it into 8 congruent triangles, or just the number of sides. Find the area of one triangle and multiply it by 8. Absolutely valid way to do it. So what do I know about this? Well, I know the radius is 2. What that means is the distance to the vertex on the circle, because this octagon is inscribed in the circle. So the distance from the center to one of these points is 3, 3. And I also know that since there's 360 degrees here, 360 divided by 8 means this is a 45-degree angle. So I'm going to go down here and say, okay, well, I'm looking for 2 things. I'm looking for the side length, so I can get my perimeter, because I'll just take that side length times 8. And I'm looking for my apothem, which is this distance here. So I'm going to cut that up, and I'll actually do it off to the side here since I've got so much room. Cutting that triangle in half, I've got, I'll call this x, which is going to be half of that side length, the apothem, and 3. And then this is a divide the 45 by 2 and get that. So I'm going to say that my cosine of 22.5 degrees is equal to a over 3. And my sine of 22.5 degrees is equal to x over 3. So I multiply by 3 on both sides, and I get my apothem is 3 times cosine of 22.5, and my multiplying by 3 on both sides, my half of my side length is 3 times sine of 22.5. Okay, so I can go back over to my formula, plug everything in, and from here it's just arithmetic. I'll carry a little bit of this through though, so this is 1/2. The apothem is 3 cosine 22.5. And my perimeter would be, well, I know I've got this length here, x. So if I multiply x by 2, or 2x, I get a single side. And then if I multiply 2x by 8, I get the whole perimeter. So this is 16x, right? Times 2 to get one side, and times 8 to get the whole perimeter. So 16x, or 16 times, and x is 3 sine 22.5. So just simplifying a little bit, I get 1/2 of 16 is 8. And then 8 times 3 times 3 is 72. So I get 72 cosine 22.5 sine 22.5. So that's the area of my base. I will plug it in once to put it up here, but the exact volume of my shape then is 12 pi minus 72. And I'm going to write the sine first just because we do that for some reason. Cosine 22.5. That is weird. It's not alphabetical. Sine just always comes first. Interesting. But there's the exact, if we want to plug it in, we would go 12 pi minus 72 sine of 22.5 cosine of 22.5. Whoops, missing a decimal. Oh, shoot. There we go, and missing a decimal. Come on. 0.5. Let's try that again. There we go. Oh, dot, dot. Boom. I'm writing very small here. So that would be 12.243. 12.24 would be our best approximation there. All right. Well, that's going to end it for the video. I hope you enjoyed it. I'll post the notes as usual, and good luck.